Hello, everyone. My name is Pedro Magan. I'm a computer science PhD student at Simon Fraser University, and today I'm going to present human navigational intent inference with probabilistic and optimal approaches. So the problem statement that we are going to tackle in here is to compute the future state of human. As you can see in the picture, there are some path that has a higher probability given the goal. So we assume that we have a Dubins car model for the dynamic part, and then we have noisy rational model of the behavior. We assume that we are approaching the goal relatively fast, and the human will stop when it reach the goal. So the contribution that we are having in this paper is first, we're going to consider the augmented 4D set, which includes the heading and velocity in addition to the position x and y. We're going to consider utility function from time to reach and reinforcement learning. We assume the model parameters, three model parameters, which are the policy optimality, which shows how optimal we are acting with respect to the most optimal one. And then we are going to consider the navigational intent, aka the goal, and the farsighted factor, which actually shows it is insighted from the reinforcement learning discount factor. And we have the particle representation of goals in humans, and we propagate those goal particles as we goes by. And we're seeing the graphical model on the top right. So how to compute the QR based on the TTR? The TTR is a discounted Q, assuming the goal to be at origin. If you're looking at the relation of updating the actions, we can see that we have a Q and other internal parameters in here, but we are not going to consider only the distance for the Q, but we are going to consider the time to reach, which also incorporate the dynamic of the system. So how we handle the non-origin goals, we are going to use the translation, rotation, and interpolation. And for discount factor, we're using the Bellman equation. So the update rules on the particle filter, we are going to use the Bayes rule. As you can see, we can look at the likelihood and then the prior knowledge in here. For the particle filter of the goal evolution, we are going to use the random walk with entropy maximizing particles. And we're also going to draw samples from the actions of the latest probability, since we don't have access to the actions. And then we also have the 4D model for the states that we're going to use the particle filters for. On the right, you can see the results of approaching the goal. At first, we have the arrows are diverged. As it gets closer to the goal, they are kind of closer and converge to each other. And here you can see on the bottom, you can see the different paths gone for the different data. And then here is the result of the particle filter convergence. The green dots actually shows the particle filter. And finally, in here, we can see the results. We applied a result for both the synthetic and real world data. For the synthetic on the table on the top left, we can see that we have the particle filter, the brute force, and the WA, which is another famous approach for this. For k equals 1 means horizon equal 1, we can see that our approach provide better result, and the brute force provide the best one. But if we increase the k to 3 for 3-step horizon, then the brute force cannot provide a solution, and we need to use the particle filter.